Nowadays, micro-unmanned aerial systems, or drones, are adapting to navigate complex environments such as dense urban settings at low altitudes, and detecting them has become crucial with their widespread use, particularly in military applications. The existing detection methods require a line-of-sight path. However, we need a non-line-of-sight detection scheme for an urban setting. So, our objective is to develop a continuous wave Doppler radar system to detect different types of drones operating within a densely cluttered urban setting. This is the system overview: a single TX chain and 4 RX chains that are sampled simultaneously through a microcontroller. The signal processing and machine learning algorithm is running on computer, which can be accessed using a simple user interface. Considering the transmitter-receiver architecture, we have a VCO to generate the stable continuous wave at 2.47 GHz, which is then amplified and split for transmission and mixing at the receiver. In the receiver, the received signal undergoes amplification in 2 LNA stages. Then it's mixed with the transmit signal, which produces the IF signal containing the Doppler shift. This is extracted using a baseband filter and further amplified until we can sample it using an A to D converter. Now let's look at the hardware design. The antenna configuration uses single input, multiple output. By opting for a single fed transmit antenna array, mutual coupling was reduced. This enables us to use the same design for the receiver, further reducing costs. Dolph-Chebyshev tapering was applied to reduce side lobe levels and improve gain. The antenna was designed in ANSYS HFSS, showing a narrow 21-degree beam width and a sufficient gain of 4 decibels. 1 antenna is used for transmission and 4 for reception. We implemented 2 versions of transmitter PCBs as part of this project. The first iteration was a 4-layer PCB with impedance-controlled RF paths and an unequal Wilkinson power divider to divide the power for the transmitter antenna and the LO for the receiver's mixer. The second PCB was an improved version with the power divider replaced with a 2-way RF splitter module and a more stable voltage reference to the voltage generator VCO. The receiver PCB design was done in 2 iterations too. The first PCB version was of 4 layers and a Wilkinson power divider to split the LO for the 4 channels. The second PCB was designed as a 6-layer high-precision board with a 4-way splitter module and better isolation between the RF and the IF sections. The IF stage was improved with reconfigurable circuit topologies for better flexibility. Now let's look at the signal processing and machine learning chain used to detect different types of drones. After the signal is captured by the local machine, the raw digital signal is sent through multiple signal processing chains and a machine learning model to get the final output. After denoising and normalizing the signal, a special signal processing function called spectral correlation function is used to get the spectral correlation density of a given signal. In our work, we have used the FFT accumulation method to efficiently calculate the spectral correlation density. It involves multiple stages of windowing, obtaining Fourier transform, applying autocorrelation, and again applying Fourier transform to capture the cyclic nature of the frequency domain signal. A comprehensive guide on how to implement spectral correlation function is available on the reference links shown in the slide. With the processed signal as the input, a machine learning model is trained to detect the presence of drones. Since the spectral correlation density of the input resembles an image, we are using a convolutional neural network as our detector. Specifically, we are using a state-of-the-art EfficientNet B0 model as the backbone of the neural network. A set of additional layers are used before and after the EfficientNet feature extractor to alter the network according to our needs. Further implementation and training details are displayed in the slide. Now let us look at the experimental setup and the results we have obtained. One of the main challenges we faced during the project was the unavailability of a dataset. Therefore, we created our own dataset by collecting data in line of sight and non-line of sight in both indoors and outdoors to imitate the densely cluttered environments. Different kinds of drones were placed in a distance ranging between 2 to 5 meters and an angle between plus and minus 90 degrees. These are the spectral correlation density maps we observed in outdoor for varying range. As shown here, the intensity of the SCD pattern decreases with increasing range. These are the spectral correlation density maps we observed in indoors for varying range. Similar to outdoors, the intensity of the SCD pattern decreases with increasing range. However, The mean intensity is higher compared to outdoors because of receiving more reflected signals by the denser clutter. This is a comparison between the SCD patterns observed for line of sight and non-line of sight with the no-motion scenario as a reference. The SCD pattern in non-line of sight is weaker than in line of sight. However, the emerged pattern can be fed into the machine learning model to identify the presence of the drone and the drone type in non-line of sight. A total of 5 different types of drones are utilized when gathering data, with 2 having carbon propellers to increase the reflection intensity of the signal. Here you can see the patterns generated by each of the drones. Finally, here are the results. We have been able to achieve an overall of 87% recall from our machine learning model. This is our team and our supervisors. Thank you.